This is 30th lecture and our topic is all pass realizations. In the last lecture we had ended up for the first order all pass filter H of z equal to 1 plus d1 z inverse d1 plus z inverse. We had ended up in identification of the transmission parameters T11, T22, T12 and T21. We had only taken 4 of them, there are many other choices. For example, I could have taken this as plus, I could have taken this as minus and this also as minus. Okay? That is another realization. All these realizations are different. We also pointed out that A and C shall have transposed relationship with respect to each other, and similarly B and D are transposes of each other. Let us take choice A and look at it closely. Choice A says that y1, y2, the transmission parameters, mind you, z inverse minus z inverse T11, T22, T12 is 1 minus z to the minus 2 and T21 is 1 multiplied by x1, x2. Therefore, I can write the equations as y1 equal to z inverse x1 plus 1 minus z to the minus 2 x2 and y2 is equal to x1 minus x2 z inverse. Now, if I, these are multiplierless, have to be, that is what we wanted. But you see, if I realize this directly, we shall require 2 delays, whereas we want only 1 delay. So, we have to do something to reduce it to 1 delay. You notice that if I multiply y2, if I multiply this y2 by z inverse, if I multiply y2 by z inverse, then I get z inverse x1 minus z to the minus 2 x2. Both of these terms are present in the first one, isn't that right? In addition, in the first one we have an x2. So, I can write this as x2 plus z inverse y2. I can realize y2 by 1 delay, then I require to construct y1 from x2 and z inverse y2. If these 2 delays can be shared, then we have done our job. Okay? So, if I want to construct this, it has to be done with a little bit of care and thought. I have x1, I add it to x2 z inverse minus x2 z inverse. The minus is taken care of here, and then I have a z inverse. I can't avoid 2 delays, looks like. Okay, we will see later. Let us have the realization z inverse, and then I require an x2. All right. This will give me y2. Agreed? x1 minus x2 z inverse will give me y2, but y2 and x2 are related by the multiplier d1. Agreed? this was a digital 2 pair terminated in multiplier d1, that is x2 is d1 times y2. Okay. Finally, we construct y1. For y1 we require x2, and z inverse y2. Is there any way that I can avoid this z inverse?
There should be multiplier 1 by d1 after z inverse, above g inverse, and then add x2 with 1 by d1.
Here?
No, in z inverse.
This one?
Yes, sir. Above that, there should be 1 by d1.
Why?
So then we can write y2 z inverse. And then add it with x2.
No, that will not. Perhaps you are right. I am not catching. What you want to do is put a 1 by d1 here, is it?
Yes, sir.
Okay,
No,
let's
sir.
see.
There should be
Here?
sir, there should we should
Oh, from here,
branch from that point, sir.
this point.
Yes, sir. Branch from that point.
Okay, branch from this
1
point.
by d1. 1 by d1 and add this with
If I
y2.
take 1 by d1, then I get y2.
Yes, y2 z inverse.
What are you doing now? You are increasing the number of multipliers. You require a d1 and a 1 by d1 here. That's worse. That's worse. Multiplication by 1 by d1. So that's not a solution. You can try others. If you can find out a modification of this so as to have only one delay, you have done an original work.
We should shift d1 after z inverse. About
Try the solution and let me know. Okay. If you can do that, you have done an original work. So this is choice A. Let's consider choice B. Choice A requires 2 delays till I get a solution from this gentleman with 1 delay only. Therefore, A transpose shall also require 2 delays. There is no point in investigating A transpose. So, investigate choice B. In choice B, y1, y2 is equal to z inverse minus z inverse 1 plus z inverse 1 minus z inverse multiplied by x1 x2. So let's write the equations for y1 and y2 and try to do some manipulation so that we can get we aim at 1 delay. One multiplier has been assured because we have taken this out. It is a multiplier extraction, and therefore we have y1 equal to z inverse x1 plus 1 plus z inverse multiplied by x2. y2 is 1 minus z inverse x1 minus z inverse x2. And if you notice carefully, if you look at it through an observer's eyes, you notice that I can write this as x2 plus z inverse x1 plus x2. Agreed? We can write this as x2 plus z inverse and this as x1 minus z inverse x1 plus x2. Agreed? Now the road to a single delay has opened because I can do with these two are the same quantities. All I shall require is a multiplier by minus 1 and both of them can be realized with only one delay. Okay. And if I now draw the diagram, it would be slightly involved, so try to draw with me. X1 summation x2. First we add x1 and x2 because this is what we require, then we delay by one sample. So, I have gotten the term Z inverse x1 plus x2. Okay. I have to add it, well, I have to multiply this by minus 1 and then add to x1, right. I have to multiply this by minus 1 and then add to x1 to get y2, add to x1 to get y2, and I know y2 and x2 are related by the multiplier d1. So, I use a multiplier d1 to construct x2. I have not yet constructed y1. y2 was not my objective. My output is y1, but y2 I have to bring because I have to show the multiplier somewhere. y2 and x2 are related by the multiplier d1. Now I construct y1. y1 is x2 plus z inverse x1 plus x2, and that is available here. So, I bring it out here and this gives me y1. This is a single delay, single multiplier structure, single delay. So, it is canonic in multiplier as well as delay. All right. This is a very beautiful first order structure, first derived by Mitra following his concept of digital two pair. Normally it would not occur to one that one can draw such a structure. The transpose of it, which is the choice D, B and D are transposes of each other, is equally applicable. And you see, the virtue of this is that even if D1 changes, it can change due to various reasons, the all pass property is maintained. Okay. Magnitude shall still remain 1, the phase shall deviate, the delay shall deviate, but only to a reasonable extent. The magnitude, there will be no magnitude distortion. Okay. Similarly, if I consider a second order transfer function, now a second order transfer function, I can have of this form 1 plus d1 z inverse plus let us say d1 d2 z to the minus 2. In other words, the coefficient of z to the minus 2 I express as a multiplier of d1. Then my numerator shall be d1 d2 plus d1 z inverse plus z to the minus 2. And if you proceed in exactly similar manner and be lucky, then you shall be able to lucky, because there are so many choices. Which one shall lead to 2 delays and 2 multipliers, you do not know. This is a second order structure, you require 2 delays and 2 multipliers. And if you choose T11, T22, T21 and T12 properly, you should be able to arrive at this structure. Please draw this structure with me. I will draw it on another page. X1 summation, then I draw the 2 delays, Z inverse and Z inverse, and then a summation, the output is Y1. Now comes the manipulations. From this comes a summation and then the 2 multipliers. The multipliers are D1 and D2. The multipliers are D1 and D2. This comes from a summation having two inputs, one is this and the other is x1. Then this is multiplied by minus 1. In some ways it resembles the first order. Okay? There was a multiplier minus 1 here, but I leave it to you to find the trick, how to find this structure. And then this signal goes to the last summer. Excuse me. I hope I have drawn it correctly. Yes, that's it. I hope you have been able to draw straight lines. I have drawn them as curves because I have to restrict it to the page. One might ask at this point, well, this is a 2 multiplier. The multipliers, can you call it a direct structure? No, not quite, because the coefficient of z to the minus 2 in the denominator is d1 d2, whereas your multiplier is d2. So it's an indirect, but it doesn't matter. We have been able to do it 2 multipliers. Now one might ask here, why didn't you take the usual form, that is 1 plus d1 z inverse plus d2 z to the minus 2, then d2 plus d1 z inverse plus z to the minus 2. Why didn't you take this form? I didn't take this form to start with because derivation of the other one is easier than the derivation of this. This can also be realized with only 2 multipliers, and the realization, please draw with me, is as follows. But it's slightly more involved to find out this structure. I encourage you to find this structure. x1, it is very similar to the previous one, z inverse, and finally a summar output y1. This is what we draw at the beginning. Then in the previous one, this junction signal came to a summar directly. Now it comes through d1 to a summar. And to this summar, in the previous one also there was a multiplier minus 1, here also it is minus 1, and the output of this, output of the previous summar came to this point through a multiplier d1. Now it comes directly. Directly. The multiplier d2 remains in its usual place. This comes to a summar, the output of which is this, and this summar, as in the previous case, the two cases are very similar, gets an input from x1 and this goes to the last summar. So it's simply the positions of d1 and d2, which d2 remains in its usual place, only d1 changes its place. From a horizontal one it has gone to the vertical one. But you can of course analyze and show that they represent the given transfer functions. But to get the structure from the given transfer function, you shall have to sweat a little, and I suggest that you do that.
Excuse me. The structure that we have realized contains a loops.
Which loop? No delay free loop.
So will the structure be stable?
Yes. If the structure in any loop, if you have a delay, then it will be stable. If you have a delay free loop, then you have to be careful. I hope there are none in this too. Okay. Shall we go and discuss third order structures also? How about that? Third order all pass or fourth order? No, we don't. Why not?
Because it can be less.
Because a third order is a cascade of first order and second order. So, realizing first order and second order all pass canonically with regard to multipliers as well as delays suffices for all pass orders. Okay. Now, the next topic would be the same, that is all pass realization of IIR all pass realization, but by a different approach. This was multiplier extraction. Now we say if I have any arbitrary order all pass, let us say mth order, let us write AMZ as equal to 1 plus D1 bar Z inverse plus etc. plus dm bar. The reason for using the bar you will see later, it is just a symbol. You could use some other symbol. Z to the minus m, then dm bar plus dm minus 1 bar, Z inverse plus etc. plus Z to the minus m. Let us consider an mth order all pass function. Now, we can of course realize this as a cascade of first order and second order all pass filters, but that requires factorization of the denominator. Isn't that right? Is that correct or not? Realizing this as a cascade of first order and second order, you shall have to factorize the denominator. Do you have to factorize the numerator also? Yes or no? No, because they had this relationship Z to the minus m dm Z inverse. Okay, so you have to factorize the denominator. Now, in digital filter realization, one always wants more structures so that he has a choice which one has the lowest overflow and which one has the lowest quantization error. And therefore, we look at this whether it is possible to do a realization of the mth order all pass filter without factorization. And the approach that is adopted for this is D2P. Instead of extracting the multipliers as we did in the first order and second order, we extract D2Ps, digital two pair extraction method. In other words, what we do is we take a digital two pair and terminate in a m minus 1 of Z to get a transfer function of a m of Z. Do you understand the approach? That is, we start with AMZ, all right, then we construct a digital two pair which is terminated in its one lower order transfer function. Then I shall repeat the process. AM minus 1Z I shall take and realize as a digital two pair terminated in AM minus 2Z and so on. You understand? It is an iterative process. This will not require factorization and it will give an alternative structure. What will be the last? Now we have to show that at every stage we shall get an all pass. At every stage, that is AMZ, when we realize as a termination of AM minus 1Z, we shall have to make sure that this is all pass. And we already know a procedure, don't we? In IIR stability analysis, stability testing, we know a procedure. So can we apply that procedure to get a realization, an alternative realization of the IIR all pass filter of any order? It turns out that the structure that you get has been quite well known in statistical signal processing, and the structure that you get is a lattice, and for some reason lattice has been found to be very suitable for VLSI implementation. That is, DSP chip you can implement in VLSI if the realization structure that you use is a lattice. Okay. So, and it was Mitra and his student Vaidyanathan, who is a professor at Caltech, who found out that this same structure can be derived from digital two-pair extraction approach, and this approach is the simplest approach to derive a lattice. Lattice was derived in statistical signal processing in a very different manner, in a very complicated manner. This is much easier to understand. Let us look at it. For this we recall the stability testing procedure that we had adopted for an all-pass filter. For a general filter, but we constructed an all-pass filter with the denominators is the same. Okay. So, what we did was, starting from AMZ, we derived a set of filters AM minus 1Z, then AM minus 2Z, and so on up to A1 of Z. What is A0 of Z? 1. Okay. And we tested the factors Km. Km is the same as the coefficient of Z to the minus m in the denominator. So, Km is the same as dm, and the structure is stable, the transfer function is stable if Km is less than 1 for all m. Agreed? This is what it was. How did we derive the lower order from the higher order? The relationship was AM minus 1Z. Let us recall the relationship. This was equal to Z AMZ minus Km and 1 minus Km AMZ. Where small m goes from capital M to 1. Okay. Small m, that is, we start with the capital Mth order, then the lower order, and so on. And this relationship, well, how do you find Km? Km is dm, which is the same as Am of what value of Z? Mentally, you construct the structure, construct AMZ. AMZ is 1 in the denominator 1 plus etc., and the last coefficient is dm. What is the numerator? Dm plus. So, if you want to get rid of all of the terms, you put Z equal to infinity. So, Km is Am of infinity. Okay. And in addition, in this relationship, the coefficients are related to each other. The coefficients of Am minus 1 and Am are related to each other by this relationship. That is, if the coefficients in Am minus 1Z are denoted by di prime and Am of Z by di, you understand why I put that bar to start with? To distinguish from these two. Okay? I want to keep the relationship simple. Di prime is equal to di minus dm minus I divided by 1 minus dm squared. Agreed? Where I goes from 1 to how many coefficients? M minus 1 obviously, because it is di prime. This was the stability testing procedure. We shall use this now very judiciously to now our aim is to construct AM of Z. Let's go back a little bit. As the transfer function of a digital 2-pair terminated in AM minus 1 of Z, right? Terminated in AM minus 1 Z. I have not shown as a block because this block is again realized by another digital 2-pair, another digital 2-pair, and so on. Important point to note, what is the last all pass function? 1. What does it mean? That in the output y2 should be connected to x2 through a transfer function of 1. That means they are directly connected. Okay, so this cascade will be terminated in a straight connection. All right, this point should be obvious. So in order to construct this digital 2-pair, in going from mth to m minus 1th stage, I require to identify its transmission parameters. All right. So I require a relationship between AM and AM minus 1. In other words, I have to invert the relationship between AM minus 1 and AM. And this relationship is AMZ, very simple algebra, is equal to Km plus Z inverse AM minus 1Z divided by 1 plus Km Z inverse AM minus 1 of Z. Now the digital 2-pair, if the digital 2-pair, mth digital 2-pair has the transmission coefficients T11, T22, etc., then obviously this should be the same as 1 minus T22 AM minus 1Z. I am writing the transfer function of a terminated digital 2-pair, and in the numerator we have already done this, T11 minus T11 T22 minus T12 T21 multiplied by A M minus 1 Z. Agreed? So I compare these two and identify the transmission parameters. Obviously T11 should be equal to Km. Agreed? T11 should be equal to Km because AM minus 1Z occurs here. T22 should be equal to minus Km Z inverse, very good, and T11 T22 minus T12 T21 should be equal to minus Z inverse. Okay, that is T12 T21 should be equal to, yes, 1 minus Km square multiplied by Z inverse, right? So I have got T11, T22, I fixed them, and I have got the product T1 to T21, and now I can play with these individual factors. Let's list some choices, okay? Some choices for T12 and T21, exactly like we did in the first order all pass case, and then investigate some of them at least. Some possible choices. Let's make a table T11, T22, T12, T21, and let's list these choices as small a, small b, small c, and small d. T11 and T22 are fixed for each of them, Km and minus Km Z inverse. Then instead of, we know the transposition business, so we will not use transposition. If we can find one, we can find the other also. So let's list some different choices. One is that for T12 we choose 1 minus Km squared Z inverse, then the other one should be simply 1. Agreed? I can also choose 1 minus Km Z inverse, and this one is 1 plus Km. I can choose this as square root of 1 minus Km squared Z inverse, then this would be square root of 1 minus Km squared. I can choose this as Z inverse, then the other one shall be 1 minus Km squared, and I can go on doing this. Okay. Now these 4 choices contain the structures of our interest, and therefore we shall go into this. Our aim would be to realize T11, T22, T1 to T21 in as simple a manner as possible, in a canonic manner. What does that mean? We should be able to use only one multiplier and one delay. Agreed? Let us see what we get. Consider choice A. In choice A, we proceed the same manner. Y1, Y2 is equal to Km minus Km Z inverse 1 minus Km squared Z inverse and 1. Y1, Y2. I beg your pardon. X1, X2. So I write these relationships. Y1 equal to Km X1 plus 1 minus Km squared Z inverse X2. Have I made a mistake? Not yet. Y2 is equal to X1 minus X2 Km Z inverse. In the same manner, if you look at Y1 and Y2, you see that Y1 can be written as X Km Y2 plus Z inverse X2. Very good. Km Y2 plus Z inverse X2. Let's look at these relationships and try to construct them. That is Y1 equal to Km Y2 plus Z inverse X2 and Y2 equal to X1 minus X2 Km Z inverse. Our 2 port is X1 Y1, then we should have Y2 and X2. Okay. You notice that in both of them we require Z inverse X2. Okay. So X2 we delay by one sample. X2 we use a Z inverse. And then to construct Y1 we require Z inverse X2, we require this input and Km Y2. In other words, we require from Y2, we will see how to construct Y2 later, we require this multiplied by Km. Okay. Y1 is Km Y2 plus Z inverse X2. So we have constructed this. Then Y2, how to construct Y2? Y2 is X1 added to minus Km X2 Z inverse. We have it here, X2 Z inverse. So this has to be multiplied by minus Km, and this is what is Y2. Agreed? But we have not achieved the purpose. We have still used two multipliers, Km and minus Km, and it suffers from the same problem of word length or quantization error. It is possible, well, you see that the total structure will be simply cascades of such structures, ultimately terminated in 1. Okay. This, in our future reference, I would not like to draw this again and again. This block I shall simply represent as Km. Okay. This block I will not draw it again and again, I will simply represent it by Km. Now we shall see that it is possible to derive a single multiplier structure. It is possible to derive a single multiplier structure, but for some reason which I couldn't find out, this structure has been favored over the single multiplier structure. This is called a lattice. For some reason which I do not know, this structure is favored. That is with two multipliers, Km and minus Km. One of the reasons can be that if it is a software program to realize the all-pass structure, you know, the difference between software and hardware is not relevant if you use a PC, a host PC to interface with your processor. All calculations can be done there and you can transfer it there. But anyway, this is favored, so this is what we shall use, except in special circumstances of tunable filters. When we construct a tunable filter, we should not have more than one variable in a first order filter. We should not have more than two variable multipliers in a second order filter. Okay? And there we shall use the realizations which use canonic multipliers. But for some reason, as I said, this is preferred and therefore we shall denote it by Km. To get a single multiplier structure, we consider choice B. Consider choice B. Choice B, y1, y2. If you recall, we have Km minus Km Z inverse, 1 minus Km Z inverse, 1 plus Km multiplied by x1, x2. If they are expanded, then you get y1 equal to Km x1 plus 1 minus Km Z inverse x2 and y2 equal to 1 plus Km x1 minus Km Z inverse x2. If I define, now comes the question of application of gray cells. You have to look at them very closely and see that if I define a variable v1 as Km x1 minus Z inverse x2, agree? Then I can write both of these in terms of v1 and x1 or x2. For example, y2 is simply x1 plus v1, agreed? No multiplier here. That's the key. No multiplier here, x1 plus v1. Multiplier is here. Then I should be able to do this. Please understand the thinking that has gone behind this. You see, the multiplier I have used to construct v1. So to construct y1 and y2 I should require no multiplier. That is the concept, that is the thought. And indeed you can see that y1 is v1 plus Z inverse x2, no multiplier here. Agreed? So one multiplier has done the job. Now the realization. Let's look at the realization. We have y1 equal to v1 plus z inverse x2, y2 equal to x1 plus v1, and v1 is km x1 minus z inverse x2. To draw the realization, we first draw the x1, y1 lines and y2 and x2 lines. Our digital 2 pair is between these two terminals. We require a z inverse x2, so we use a delay z inverse. And then we require to construct first v1. Okay, so v1 is x1 minus z inverse x2. I have z inverse x2 here, so I multiply by minus 1, not a multiplication. Then the result I have to multiply by km. So km comes here, and this is v1. Agreed? Once I have constructed v1, then the construction of the other two, for example, y2 is simply x1 plus v1. So v1 goes here and x1 comes here. Okay, to get y2. And to get y1, we require v1 with z inverse x2. So I require an adder here, z inverse x2, and then v1 comes directly here. Is it okay? Single multiplier, single delay, and therefore this is indeed a canonic structure. One reason that I guess why this structure is not popular in comparison to the two multiplier structure is because there is a crisscross here. There is also another line here. Perhaps this poses problems in, I am not a VLSI expert, perhaps this poses problems. I do not know. Where is the delay free loop? X1 to y1. There is no delay free loop. This arrow is in the other direction.
x1 to y2.
X1 to y2. No, there is no loop. The arrow. This is why the arrows are so important, to show the direction of signal flow. There is no delay free loop. If it was, then this structure would have been invalid structure. As an example, a third order structure, third order all pass function can be realized by three blocks like this. First will be K3, then K2, then K1, and do not forget about this, this would be terminated like this. So this will be A3Z. Obviously, K3, K2 and K1 have to be derived. How? By using that relationship, that is di prime equal to di minus dm minus I divided by 1 minus dm square. K3 obviously is given. K3 is the same as D3. So you have to derive K2, K1. Okay? And if in the process one of these exceeds 1 or is equal to 1, then you need not proceed further, because the structure is unstable. There is no point, you cannot realize the transfer function. Okay? We shall stop here and continue next time.